Well, welcome y'all, and really excited to have Markus come here. I've been trying to get him to come for a while here. It's been a little bit difficult, but we finally got him to arrive. And he did a lot of cool stuff. Like I think one of the exciting things he won't talk about today, but this game of life, which is quite exciting. But you guys could Google it at some point. So Markus comes all the way from MIT to tell us about his research. Not very good introduction, so I think I'll stop there. So yeah, thank you so much.
Yeah, thank you so much. Well, thank you so much, and thanks everyone. You know, it's quite exciting to be here at MIT. It's been a couple of hours since I was here. I guess I was here all day, but you know what? I'm gonna actually mute myself because I hear myself. Sorry about that. And I also will probably remove my video stream as well because it's really confusing. You need to make this sound. Yeah, perfect. Okay, that's awesome. Oh, it's still there. There's a little trick here. Okay, is that better? Oh no, I'm so sorry. We should have tested this.
Oh, you're.
Hello? Okay, now it's gone. Great.
Okay, let me check, make sure I can hear.
Yeah. 1, 2, 3.
Yep.
All right, great. So now, okay, so let me now quickly just, okay, so I don't see my video stream. Well, anyway, thank you so much for the invitation, and I'm excited to be here to, you know, really share some of the things. Yeah, sorry, it's like, no, it's not. It's a small problem, I think. Okay, here we go. No? Okay. Yeah. Oh, here we go. Yeah, just need some sort of wake-up call or something. All right. So yeah, thank you very much for coming. And so I have you know, various materials, mostly related to proteins and materials modeling, but also some other stuff. You know, in the interest of sort of broader discussion. And yeah, most of the stuff we do deals with protein materials in my lab. We are interested in connecting the scales, and we are mainly looking at materials from proteins like silk and, you know, various technologies derived from that. So we're not just looking at single molecules, mainly we're looking at materials, and we're really fascinated with this problem of connecting the nanoscale to the macro, both understanding and also designing protein materials. And I think, you know, we all share that passion here from many different directions, probably. It's a huge problem. And so, you know, if you're looking at, this is a spider web at the microscale that we've imaged in our lab, and on the right, so you see it's actually a collagen molecule. It's not a silk molecule, so you know that. Usually the audience might not see the difference, but anyway, it's just to show you, you know, obviously there's a lot of structural complexity here at every scale. And so what we've been struggling with in modeling is that, you know, we really can't, solve this multi-scale problem very easily. And the way we've been doing it for, I would say, you know, decades, is that we try to predict the macro scale properties of something like a tissue or a spider web by essentially solving some partial differential equations that we have to integrate in space and time to actually get to the large scale. And that is not easy. And in fact, especially when we're doing design problems, right, you invert the problem, you really can't really brute force your way out of that. And so we have been thinking about different mechanisms and strategies to solve this problem. Obviously, artificial intelligence has helped us to maybe, you know, tackle some of those really grand challenges in understanding, but also modeling things like proteins and protein materials in a little bit different way. So now there's a lot of sort of stuff going on, of course, in the field. And one of the things that I sort of to clarify, right, is that, you know, if you use conventional machine learning, you are always faced with this challenge. You really cannot extrapolate significantly beyond your training data, right? The model has really no understanding, right, of what is going on. It's just fitting, you know, nonlinear curves to the data. And if you want to go to, you know, spaces outside of your training data, usually we fail. And that is actually true for many things, including, you know, folding predictions, right? So you can very easily find proteins that will not be, you cannot fold them using conventional or current folding techniques. So this is something that we have to be mindful. That's why the title was sort of about physics awareness. We want to build in, you know, models. We want to build models that can understand something a little bit more about physics, okay? And they can actually do what I want to do on the right-hand side, what I show here, and that is really have sort of the vision for this is that you have a scenario where you have some data, right, some observation, maybe some theories even, But you really can use the models to predict things in spaces where you have no data or very little data or actually no data at all, and you can really make discoveries and maybe design things that we have never seen before. And this is not just limited to the observations or maybe predictions and design, but also, of course, for just the very process of scientific discovery itself. We think we can model that actually as well. So that's our long-term goal in the lab, and we do this by translating this problem of let's say a protein material like silk. And as you can see, silk is obviously my favorite protein material, and collagen. But these materials are usually, you look at them in a sort of a geometric Euclidean space of hierarchies and relationships. This is sort of what gets us in trouble because we have to brute force ourselves out of that. And if we don't brute force model, we have to coarse grain and reduce the degrees of freedom. But there are issues because we're losing details that actually matter because these systems are really hierarchical. So in other words, you can't encapsulate function at one scale. They actually have cross-scale relationships. So what we do instead, we model this whole thing as a graph, right? And so these graphs allow us to really understand or model the relationships in a much more abstract way. So I can actually understand that maybe a single point mutation has a certain effect at the macro scale in a disease or in a tissue or in a spider web. And I can actually begin to really build these relationships, model them. And this has other implications, actually. So we can build, this is an illustration of how we use graph methods, specifically based on category theory, which I've worked on for a long time. So this is actually my origin in getting into, today we call, AI or machine learning or generative methods. About 15 years ago or so, we worked on this with David Spivak, Elizabeth Wood, and others, and we built categories, graphs, essentially, of knowledge. And we did this not only to describe materials, but also to create isomorphisms and relating different systems. So relating something like a protein and music, or language and proteins, and many other things, of course. And so this actually was the origin of what we've been doing. And this is sort of laid dormant for, I would say, 10 years because we didn't make any progress. We couldn't figure out how to build these graphs for real data. I mean, other than us understanding something and building a graph, which is a toy problem. And the last couple of years, we figured out how to do this at scale. And this is sort of what we're doing now, building models of this. And this is, I think, very exciting. And so, so the idea is just as a motivation. I actually get back to this at the end. In the reason why we're building these graph models is not only to have a very sort of mechanistic, abstract representation of how things work, symbolic relationships that, create representations of function, but also that we can create isomorphisms. What this means is that you have a structure of a graph that describes a certain function like robustness or strength. And you can actually, create these representations for many different systems, and you can map them, right? So if you have a certain structure in a graph, you might find that this structure appears also in the same or in a similar way. You can relax, of course, the way you're creating isomorphism detection. And you might find that, something like this structure appears in music, but also appears in proteins or in materials. And this allows you to do really fun stuff. So I'll get back to this later on in the talk. Now, what we're trying to do is to figure out if we had these, ways of actually, taking information, and this could be individual measurements or maybe a simulation or a theory, an equation. And what we're really trying to do in our AI modeling strategy is to use bits and pieces of information and connect them in the context of what we're asking the model to do, right? So we're solving a boundary value problem, or we're maybe solving a design problem. So we're going to have different connections, but this is always the idea, right? You're connecting bits and pieces of information and make predictions. This is what the model learns, and I will talk about this several times through the presentation, of course, but take information, we connect them, and then we hopefully make some smart decisions, predictions from that, like designing something or designing a new experiment and things like that. And then a lot of times like I mentioned earlier, we work on materials, so our application is really, using peptides and proteins to build, filtration devices or, for clean water, sustainable materials, biomaterials, infrastructure, you name it, right? So we're looking at material scales, even though a lot of the stuff I've talked about, of course, can be used for many other things as well. So now what is sort of going on in this kind of modeling, and why is it different from how we've been doing things for many, really decades? And that's the following. So this is a simulation of ductility or deformation in copper. This has nothing to do with proteins, actually, but the idea is that in order for you to solve this problem and seeing how a piece of copper deforms and breaks, ultimately, we build a model of the atomic interactions, which is the potential, and the same is true for proteins, of course. And then you say, and this is a graph as well, except this graph is spatially localized. So it's basically saying how neighboring atoms interact, like in a force field, like for charm, things like this. And to actually get this, you have to integrate this for many steps over time, and also spatially integrate oxidative interactions. And you can get this beautiful movie understanding the dynamics of fracture or protein folding, you name it, anything like this. But it's complicated and expensive. So what we're doing now, right, is to say we don't. I mean, this is a little provocative crossing out. We don't actually want to cross it out, but we don't want to necessarily rely on this only, right? We want to say, okay, can I make another constitutive law governing equation, a theory that is based on these graphs, that describes kind of what's going on here, but not atom by atom. And I think this is a shift in the way we're looking at physical modeling, biological modeling, has a lot of potential. Because it's no longer that we're relying just on a theory that I have come up with as a human, but actually I can let machines discover theories, relationships between building blocks. And as I'll show you in a second here, actually the building blocks in this kind of framework in a graph, it's not limited to really one modality. So I can have graphs that describe, actually category theory was originally developed to describe algebra, mathematics, but they can also describe so equations, right? Symbols, logic. They can describe numbers, of course. Sequences, they can describe all the different kinds of things. And so with this way of creating graph representations, I can actually begin to integrate a lot of these different areas that are totally not connected conventionally, right? Because there are different theories, and I have to choose. Like in the past, do I do numerical modeling? Am I doing theories, equations? But now I can actually have theories that actually encompass all of these different perspectives. And well, I don't have to convince you of this, but obviously it's important for design because you have huge design spaces. And I mean, excuse me, I could have probably removed this, but so there are essentially, a lot of possibilities in how you can design a protein, right? So you have to figure out to narrow the design space or give you solutions maybe that are, more likely to work in the lab or clinically. Okay, instead of exploring everything. And so this is what the role of generative modeling usually means for us, is we want to create candidates that we can make in the lab. The other thing that I think, especially from a materials perspective, and these are all things we've worked on, like brittle bone disease or rapid aging disease with Chris Dahl at Carnegie Mellon. These are all diseases or, conditions where mechanics is important. There's something I do work on mechanical failure of materials. So these are all problems that have to do something with breaking, right? But also, these are all phenomena where you have a mutation that's very small, and and it creates this disease either very long time in the future, like in rapid aging disease, or in bone. Yeah, it's a small mutation, a particular mutation that creates brittle bone disease, and those are the kinds of problems I'm fascinated with, and fracture per se as well. Generally, where you have maybe a couple of things going on at the cracked tip that determine how things will break, like even a glacier might break, or earthquake might happen. And these are all problems where you cannot average your degrees of freedom. You can't say, yeah, I'm gonna basically take 1 million atoms at the cracked tip and I'm just gonna average out how they behave. It doesn't work, right? The whole point is that in fact it's only a few atoms or one mutation. And so this is why we can't average. So a lot of the traditional engineering theories of using coarse graining and kind of building things up like this doesn't work for a lot of these problems. And generally in physical systems can't do it. So that was an exciting time because we have sort of the framework, the understanding of how to build these models. Now, they're computationally intensive, and that's why we need cheap compute. So we luckily have this Kurzweil prediction, which seems to hold. I don't know. I mean, he has this prediction, apparently it's very good, that, so it basically talks about how cheap compute is, and it goes sort of in sort of a scaling law over time. And this has resulted essentially in the fact that we now can build pretty big models, neural networks or other models that kind of rival the complexity of simple organisms, right? So I think this is a squirrel or mouse is kind of what we can build today. And, in a couple of years, it might be the complexity of the human brain. And so we have to think about how we're going to use these tools, right, and these models to, advance science, not just building intelligence that maybe replaces us for general things, but also how we can maybe model, like I said, scientific discovery or building more models that are complicated. And I would say, it's real in a sense that, there are, there are real investments being made. In fact, there are companies like Microsoft restarting nuclear reactors. You might have seen that 2 weeks ago, and Google actually purchased a whole bunch of nuclear reactors themselves. And of course, Musk is building big data centers. So these are all gigantic, operations. They're totally inefficient, by the way, of course. They're, I think one day we're going to look back, it's like the first automobile, right? I mean, it's really lots of energy and very inefficient. Our brain is much more efficient, but, we are scaling, right? That's the message here. And people think it's going to work to create, artificial intelligence at levels we haven't seen. So what's the secret sauce? Well, one is scale. And the other one is this idea that I talked about earlier is kind of using lots of different information and connecting them, right? And so we do this, of course, computationally by a process called tokenization. It means we're basically ingesting in our models bits of information, and that could be anything, right? So it could be, an equation, it could be variables in an equation, it could be an algebra, it could be an interview, legal documents, books, papers, patents, simulation data, name it, right? Sequences and so on. And this all becomes part of an integrated framework that processes this information to create connections, knowledge, to make decisions, to make predictions, and then it kind of creates a process by which maybe we can begin to model or simulate the thinking process. And thinking, I would say, it's in quotation mark, right? But it is the process, right? We want to model how we think, and that's the vision we have, okay? And it's a journey to get there, but I think we all want to do that. We want to model not only that we're thinking, but models can think and have an awareness. And I'll talk more about this in a moment. But this is, you've seen this, right? So it's basically information, we tokenize, we connect this, and we build models that can hopefully make predictions. And so this is an important slide. Okay, so when you think about building these kind of models, when you, and I mean, I'm not sure, what your background is, obviously, but if you talk about what we call machine learning, typically you have something like this, or even any other modeling for that matter. You have an input, boundary condition, initial condition, and you have a model. Again, it could be any model, right? And it has a prediction. The model has no awareness of its own predictions, and that's right. The model cannot decide how good the prediction is. I mean, even PDE, Newton's laws, Schrödinger's equation. I mean, the model doesn't know how good the prediction is. We do that job. We go in, we do an experiment or check the results, and then we say, we have to fix it. Theory's wrong. Things like that. What we're trying to build, go to the right. We're going to try to build this operator that actually has some level of self-awareness. And this is again, it takes time to get there, but we are actually making quite a lot of progress in the community. So that we pose a question, we give a task, and the model doesn't just make a prediction and just like totally unaware, but actually can reflect on the prediction, and you can begin to think about it, reason about it, and then might make the ultimate prediction, which is going to be hopefully more nuanced and refined, right? So we, could be part of that, or we can let the model think about something for a long time, and then we look at the result at the end, and then hopefully it's a good result, and then we can kind of maybe, do something fun during that time while the model is doing this. But that's kind of what we're trying to build. So you can see there's going to be some internal loops and reflections going on, and so the question becomes, really, how do we build this? And I will try to talk about this now, right? How do we actually practically build models like this? And how do we even start, right? So we think that the building of intelligence or models like that is going to follow a similar paradigm as we see in biological materials in general, right? So we have in biology this universality-diversity-principle, right? We have universal features that are reused over and over in different patterns, and that's how nature creates, everything from flowers to spider webs and everything. I mean, this is really a materials perspective, but I think it's true in biology in general. And so instead of creating a monolithic, gigantic structure, it creates building blocks which are played with in different patterns, right? And this is something that we also do. I mean, of course, in language, in audio, music, all the different things are created sort of in that natural way. So we're using this approach, of course, to build better materials, but also to build the models themselves. And so the first step usually involves, thinking about how do we build some models that are very good in doing something, right? And they might not be good in reasoning or, reflecting on their own, but they're good in solving a particular task. And so this is something we can do pretty well today. And I know that probably many of you have done things like that, are doing things like this. I mean, I've looked at some of the previous speakers. There's lots of expertise here in the area for sure. In building models that can make very good predictions about proteins, for example, right? So we can build models that are very good in predicting, how stable proteins are. And this is some work we've done on collagen. So I'm just going to show some work from our lab, but there are many others like this. This is an encoder model, like a bird-like model, and that basically takes a sequence and predicts how stable that collagen sequence is. And it does work pretty well when you compare with experiment and validate. This is work with David Kaplan. We've made some of those sequences and tested them. So this is a pretty good model, in spite of having very little data. So we have methods of pre-training these models with very large sequence databases and doing a process called denoising. So this is something that maybe some of you are familiar with. So we have ways of teaching the model something about the matter of interest, like protein sequences, without knowing anything about the sequence, just by kind of deconstructing the mechanism by which they're built. And then we're fine-tuning these models to make these predictions. So this, on the left here, you see the denoising pre-training, and then you see the fine-tuning on the right. So this allows us to make models like these. We also can do design. So since the series is, I think, called design as well, right? So this is some work we've done on designing proteins by giving a constraint, like you want to maybe have a protein with certain secondary structure content, and the model will come up with sequence candidates that meet that requirement. And this is a particular model that was published last year in Chem, where we use a diffusion model to do this. Okay, so we basically have a constraint as an input, a design objective, and the model will come up with sequence candidates, and then we can compare that against the prediction with some protein folding we can do, MD simulations on top of that, so we can check how good the prediction is. We can do that. We can also we can do this actually even for residue level predictions, so we can make per residue secondary structure constraints and make predictions. And there's many other tools out there. Chroma is one of them that can do all sorts of fancy stuff. So we can design proteins, okay, to some degree, and we can keep building these very highly skilled kind of expert models on one thing, right? And so that's one of the examples. And then we can actually begin to think about how this model might be able to check itself. We can use two agents in this model. We can make conditioning, predict sequence candidates, and even have a mechanism of assessing these sequences. So this is how the model begins to maybe create some sort of ability to check its own predictions by having another model assess the quality of the prediction, solubility, or how easy it is to make it, or whether the agreement actually is with the restraint that you have in the beginning. So this is sort of one family. Then this year, we published another model that sort of does this a little bit differently to the original model. Design protein sequences directly, right? So we basically have this diffusion model that predicts sequences using a process called analog diffusion. In this next paper, we looked at not only static properties, but actually dynamical properties. So we design proteins to have a certain dynamical response. And you all know this, right? So this is Schulten and others' work, classic paper, 99 in Nature, where they pull these proteins, and lots of people have done things. We've done lots of MD simulations of that. So the idea was, well, this is a really important process in biology that you don't just look at a structure, you look at how it behaves under pressure, under stress. And how do you design for that, actually, and how do you predict how this unfolding behavior might look like? And we can do that, actually. So we built a large data set from MD simulations and then created a diffusion model that predicts these sequences. Now, these sequences actually are predicted not directly, in the sequence dimension. They're actually predicted in an embedding dimension of a protein language model. And so what this means is that we're not predicting directly the sequences, we're predicting the embedding of the sequences. And that was really key because it allows the model to learn much more about what kind of sequences are possible and what kind of relationships are likely. And that model essentially learns how to map the sequence representations and the dynamical force separation responses to the model. So this is a little technical, but I think some of you who work on this will appreciate this. And then we can solve that problem. So we can basically say, I want a certain type of response, and the model will design proteins for me that have these responses. And then we can run MD simulations to test it as well. So this is kind of like how this can be done. So this can be validated pretty well, I would say. We can even mine some of the databases we have. So this is something we're doing right now. We're finishing this paper. We have all these MD trajectories, hundreds of thousands of these that we ran. And we can actually mine them to understand a little bit more also about the physics of how these things unfold, because nobody has done these very large-scale MD simulations of unfolding. So we have a lot of data here that we're analyzing. So my postdoc, Boney, actually, he's working on a lot of these analysis, trying to understand scaling laws, if there's any kind of relationship with secondary structures, and then also using designed proteins we've made using this method and seeing where they fall on this curve. And so we can try to understand a little bit more about sort of the biophysics of proteins. So this is an example of how you can use, of course, the sequences you've generated as a way of just getting a lot more data and then there understand the physics better potentially. Why do we do this? Well, we do this because ultimately, a lot of the applications we have, as I mentioned, are in sort of engineering applications, but we do plastic replacements, super strong fibers from silk. We have a project with David actually on artificial meat, so we're creating those kinds of things. So you can see there's lots of different things where you can apply these design problems to, especially looking at a larger scale. And then there are other sort of problems we're working on. So this is work we actually are about to, not in submission, but it's kind of in submission. It's almost done. It's basically for me to submit. Let's put it that way when I have time. But yeah, so this is work where we use this technique to is pretty much the same model except different data. And here we're actually looking at eigenmodes or normal modes of motions, not unfolding responses, but the actual normal modes of the protein, which is a really good indicator for a lot of biophysical processes. And so again, here we can design proteins that have a certain, vibrational response, and again using diffusion model. And here's a couple of examples. So you can see I can demand the model to make me proteins that have a certain type of mode shape, okay, and then the model will design that for me. So this is pretty exciting. We're very excited, obviously, about dynamics because we think that's one of the next frontiers in computational modeling proteins is to design for dynamics and model dynamics and go from the static picture to something more, dynamic. So there's going to be more details on this hopefully pretty soon. Other things we can do, we can condition a model obviously to, subsets of sequences, like these are all spider webs and variations of that. And so here we have done we've developed a model that is not a general protein design model, but it's specifically trained on spider silk sequences. And there was a group in Japan that you might have seen that actually created the silkworm data set, which we have taken advantage of. This is a first measurement of very large scale silk sequences and mechanical properties. And so we trained this model to be able to model these relationships and design essentially, silk sequences for particular mechanical properties. And we can kind of pick, our combination of strength and toughness and other properties and then create sequences for that and design them. And we can also apply these types of diffusion models to other structural levels like making, silk or spider web inspired geometry. So this is kind of a merger of creating a spider web locally, but making it in a shape that are mathematically governed, for example. So these are things spiders don't build spider webs like that, right? But we can make them synthetically like this, or we can make architected materials. So this is kind of like all I had for the sort of special models. So now I want to talk about how we take these sort of specialty models that can do folding or design or predicting properties, and there's obviously a billion different kinds of things you can do to build this kind of environment, right? So this is really the holy grail, right? So because the other stuff, it's hard, but we know how to do that, and we have to still learn how to do it better. But this is really, I think, what we really want to spend, a lot of time on, or spend, at least that's the next frontier, right? Building models that can have the self-awareness and understand a little bit better about what they're actually doing. So we look at, kind of how nature creates an awareness, right? So if in the brain, of course, but also in organisms like ants, they can solve problems as a group collectively by having interactions. So these are usually nonlinear interactions of some sort, and then they can form, bridges or carry weight and things like that. They have to work together, basically. And maybe against each other and have adversarial relationships to solve problems, right, to compete, and then they come up with solutions. So one way of sort of implementing this would be to say, okay, this is the basic, simple level, right? Would you say, okay, I have a bunch of expertise, I have a bunch of experts. So usually for experts, these are kind of models with capabilities in special areas. And I can say, well, I have an expert on protein folding, I have an expert in designing a protein, I have an expert in designing for mechanics, for mode shapes, all of these things. And depending on the problem I have, I can decide, which one I want to use, right? So that's sort of the basic level of having some. It's better than nothing, but it means, there's no synergy between them necessarily, right? It's just one or the other, basically. Now, we want to do this kind of a little bit better. So what we want to do is, and I actually forgot to mention this, but I had it earlier on the slide. So what we really want to do, teach the model is not just, and I forgot to mention this earlier, but now I can mention it now. So what we really need to do if we want to have the model be more powerful than just predicting something in the distribution of training data. So we want the model to be able to not just learn the correct answer, but to learn how to develop the correct answer, right? The process of getting there, right? And so you can see, of course, by thinking about these graphs, right? This is the path we're on, because we're not just saying predicting regression problems and the model memorizes how certain distributions look like, but actually it's beginning to hopefully learn how to derive this prediction through all these relationships, that might be there, like the sequences, the patterns of sequences, the mutations and all this, to get to the answer. So we really want to teach the model how to get the answer through some sort of deduction. And there's a couple of different ways we're doing this. So here's the next sort of level up in the hierarchy of complexity, I guess. This model, we call it XLORA, does it the following way. It says, okay, so I'm making a prediction, like a number or pixel or an element in a sequence. But instead of predicting every time I'm asking the model a question, predicting an answer, I'm pausing the model, and I'm actually letting the model do two things. I'm training the model to do two things. One is I'm saying, don't predict right away. I want you to reflect on your own structure and organize yourself, like organize the different experts, and not just singularly, one or the other, but actually all the experts can be combined in a number of different ways, because these are all AI models, right? So you can combine their neurons in sort of an infinite possible combination almost, right? And we're training this model in the first step to learn how to do that. So how does the model need to organize itself to make a better prediction? And in the second step, we make the prediction, right? So those are the two steps. So thinking, basically, one step, and then make prediction. And we do this actually for all the layers, like I said, all the neurons. And what it means is this is actually when the model works and answers the question or it solves the task. You can see visually that the different layers and the different experts are combined in sort of this really interesting new combination. Sometimes it picks only one expert. You kind of see it light up here. There's this one expert coming up sometimes, but a lot of times it's really these new combinations. That's exactly what we're training the model to learn. And then during inference, it does that as well. And what can a model do? Well, this model can do, some interesting things, actually. It's a model that can, for example, do a regression problem. It can do a design problem. So I can say, design me a sequence to meet a certain constraint, or, but it can also, at the same time, answer other questions. It can basically ask, you can ask the model a question, order these sequences by the strongest one, or give me the strongest one of the ones you've computed, right? So this is a kind of a conversation you have with the model. And then you can say, well, explain why this is the strongest sequence, and the model will explain it. So all of this happens in one model, right? And so the model actually is able to create connections between all the different expertise, all the different things it begins to understand at some level. And it can do this in a single model. So it's not just there's, three different experts and you have to think about how to stitch it together, but the model actually has these connections. And of course, in some of those protein cases, we can validate this as well. So we can, build a model of the protein, fold it, do MD simulations. So we're doing some stuff like that. So we can kind of check how the model does. And it does a pretty good job. And this actually can be made even more powerful by having, processes that, are a little more complex in how the solution is developed. You can imagine if you think about this, this is a process where in fact, actually, one of the challenges with XLORA is that it's great, but you have to really kind of make your own model architecture. And it's fun to do, but it's hard, And but let's say you wanted to do something maybe that's more flexible. So this is something that we've developed more recently, where we do a similar strategy. We have a question or a task, and we deliberately do, we train the model to think, right? So not just a single step, but actually, as many steps as the model needs to think, right? And so these are mechanisms where we teach the model to deduce the answer. We also teach the model to critique itself. So it critiques how it did develop the thinking process, and then we make the answer, right? So we use all of this process. So again, we're slowing down the process, and we're giving the model more, time to really deduce. And we're teaching the model these mechanisms in the beginning based on what we think is the right way to do it, okay? And we have sort of different stages of training, and I'll show you this in 2 slides, that, we can in the beginning, we can kind of give the model some idea of how to think and how to reflect. But then in the second stage of training, we actually masking means we don't tell the model what to do. We just tell the model, you should think and you should reflect. But the model can figure out on its own how to think and reflect to give the right answer. And so I'll get back to this in a second. But these are sort of different stages of training. We can give the model something that we know, like, for example, we can give the model thousands of papers, scientific papers, and we can analyze the way people have designed proteins or materials. And we follow a certain thought process that we think is the right way, like, figuring out what are the ingredients, the processing conditions, the design principles, what's the hypotheses. I can kind of teach the model this. And then hopefully, I let the model kind of loose, right? And let the model figure out on its own how it can do thinking even better than I have anticipated the model could do. So this is what we're going to get back to in a second. But, this process is interesting because, during the training, so in this particular model, we also have another twist. One of the things that you need in machine learning AI, you need training sets, right? Here, we actually don't have a training set. And it sounds weird, right? But we have some ground truth data, okay, like scientific papers or maybe a simulation engine or an experimental engine. But we actually don't create these training data before we train. We actually create the training data while we're training. And why we're doing this? Well, we're doing this because we want the model to learn how to assess itself, okay, as the model produces answer based on its current capabilities. So we're not just telling the model, here's the right answer, just memorize the right answer. We're actually teaching the model, here's the answer you're currently producing, and here's the answer you should be producing. And then we're forcing the model to learn the distinctions between the two, okay? And so that means the model has to figure out, why are these answers different? And as the model becomes better, in the beginning it's very easy because the model is really bad, right? So it very easily learns kind of how to make better predictions. But then as the model becomes better, it becomes increasingly difficult for the model to improve itself, right? So it has to learn. It cannot just memorize. It has to actually learn these thought processes and these deductions, right? And so the model becomes very good, actually very quickly, because we're no longer just brute force training data, right? We're actually teaching the model through some very active processes. And we're doing this through multiple agents. So we have sort of these, not ants, obviously, but, kind of multiple agents that do different things. They prepare the training data during training, but also doing inference. So this is actually the inference engine. So during inference, we can use the capability of this model that has, that can make a thought process, right? And it creates a critique of itself. We can use the critique of itself to actually improve the thought process and feed this improved thought process back to the model. And we can iterate many times. And as we do this, the model gives a better and better answer successively, okay? So it kind of samples, but it doesn't just sample, right? So currently you have lots of techniques that do, sample multiple times and you pick the best answer or the most probable answer. Here we're actually actively improving the thinking process, the reasoning process, and we're doing this recursively, right? So it's very, very interesting. And at the end, we get something. So if you do this in natural language, this is how it would look like, and it's sort of a sketch, not a whole solution of reasoning, but it's a sketch you can see. So you would ask a question, right? Tell me why hierarchical structures work so well in nature and biology, and the model will try to think. So we'll have sort of go through different steps of reasoning why this is. So it doesn't just give an answer, like memorize, actually tries to deduce the answer. And it goes on for a long time. It's not the whole solution here actually, but at some point it ends, right? And then it has reflection. So it sort of says, okay, something's missing here, and so give suggestions. And then you can pause this and you can go back, and I can actually have the other agent look at the thinking process and improve the thinking process. Then I'm feeding the improved thinking process back. The model again will critique itself, right? And it repeats, right? And so the model becomes better. And then finally you get an answer. In fact, every iteration you can get an answer. And you can use these answers to, first of all, you can study them. You can see that as the model becomes sort of iterates through the recursive process, it makes better answers, which is great to see as a model. This method works. But also you can potentially integrate these answers. So you can say, okay, instead of having the final answer only, I can actually integrate all of the responses. Because what happens in the beginning, when you look at the actual answers, the answers in the beginning are not bad. It's just that they kind of focus in on one thing. Like they focus in maybe on a protein design, right? Or maybe on solvent design. But as the process goes on, they learn things are missing, right? And so they become more comprehensive. And what we can do, if we integrate all the solutions through the agent, we can actually create very comprehensive responses. They're going to be longer usually, and you can kind of pick your style that you like. But this is the process we can use. And this is sort of what I talked about earlier, right? So we have these different phases of training, right? So we have structured thinking. This is sort of how we teach the model how we think thinking could be done. And we basically give the thinking and reflection sections from the raw data. So I'm basically reading the paper and I'm letting the agents read the paper and letting the agents discover, hypotheses that the authors talked about, what materials, what sequences might be in there. And you can pick, and it's very flexible. You can pick your own method of reasoning, of course, for your problem. And then in the second phase, we mask this out. So we basically, like I said earlier, so we just give the task, the question, and we only give the answer, and we mask the reasoning and the reflection. And so now the model is very hard, right? So the model now has to give the right answer, and it actually has the freedom now to think on its own. That's kind of like the idea. So it's pretty fun. And then we can build models on top of that. So like I said, all of this is sort of hierarchical. Right? So it's kind of, we like to do things in a modular way because, first of all, practically speaking, I mean, we're not going to build, 1,000 different gigantic AI models that cost $500 million to train, right? I mean, I think at least. In reality, we're going to have expert models, and we want to be flexible for different tasks, right? In a company or an application or in academia, we want to be able to build them modularly. And also, of course, that's how we are built too, and our brain is built in the same way. So here we're taking now a bunch of those models with different capabilities, perhaps, and we build a multi-agent system to solve problems. So this is pretty fun, actually. So this is something where you can give a task like this in natural language. You might have seen this. This is something that we've done a lot recently. If you follow me on LinkedIn, you've seen maybe some of those things there. This is sort of mind-blowing to me because we started this because we said, when I give a talk, people say, oh, you're doing data-driven modeling. Oh, it's nonsense because what about all the physics? And I said, no. Actually, if I have a multi-agent model, I can combine them. This is the easiest way of doing this. I can have a model that has maybe, has learned to do regression, protein design, fine, but I also can have an agent that can write code. So in this particular example, what we did is we gave this task. You can read it, right? So it's kind of like building a potential, very simple. And the model does not know this data. It has never been trained to predict the energies of this oxygen molecule in these distances. So a traditional machine learning model would actually make a prediction. It would be total nonsense, right? Because the model has no awareness of itself. This model, though, understands that it cannot solve this problem on its own. So what it decides to do is write code. And it actually writes a code that runs some, PySCF quantum DFT, in Python, and executes the code for all the different conditions, different separations, and it does all the things I'm asking the model to do. And in the end, I get this beautiful, result. I get the table, I get the JSON, all the things I wanted it to have. I get the picture as well, the graph. And so those are kind of like multi-agent systems, and you can plug in all sorts of different agents here that you might have, right? So, I might have, 3, like in this case, or I might have more. I might have a whole group of them. I might have agents that have themselves groups of agents under them. I mean, like I showed you the reasoning model, that could be one of the agents. And here in this case, we had a protein design application where, one of the agents had sort of at its disposal a whole bunch of different AI tools like Chroma, OmegaFold, Force GPT, some of the stuff we have developed in the group. And in fact, it was plug and play. Like this was when we did this, Chroma was released at the time. And so we basically, within a couple of hours, we could make Chroma part of that mix, right? And so now I had a whole more design capabilities. And now if you give a task to these agents, they will not follow a predetermined, decision. They actually make a plan, right? So we have a planning agent that will figure out if I want to do, I want to design a protein of a certain shape. Chroma can do this. So you provide a description of what these different tools can do. Right? So we give a kind of a manual for what the method can do, and then the model will make a choice what to use and in what order. And so this is all determined by the model, right? How is it done and how is it validated and all these things, and you can solve design problems totally autonomously. Right? And the beauty here, again, is that you can actually combine, all these different other modeling techniques. Like you can connect. I don't know if I had this here. Yeah, no, physics simulators. Yeah, we had a MD engine as well. So I can connect an MD simulator, like NAMD, VMD, or VMD, I guess for visualization, LAMPS, and all these other tools. So you can actually really merge physics-based modeling, analytical modeling. You can search the internet. You can search for papers. You can search for knowledge, and so all of these things kind of come together in this agentic framework, which I think is really, really, really powerful, because you no longer have to decide, am I a data science person or am I, an MD person? Right? This all comes together. We're also building, just sort of for completeness, we're building a bunch of models in the group also for vision because, when you run these simulations, how does the model actually look at a protein as made? Well, it can look at the sequence and the structure, but You can also, it would be nice to have models that can look at a picture of this protein, right, or a picture of a graph, actually, like can look at this graph and decide whether the objective is reached and how well. So we develop vision models as well that can really understand scientific data, so not just trees and different species of animals, but also tables. So they can actually look at scientific data, understand scale bars and understand how to read out numbers and so on. And so we've trained models like these that can then do things like this is sort of not protein application, but it can do things like look at a pollen particle and you can give it a design job to to analyze the image, but also combine this with a design object like creating a tough material, right? And so it will create something new, and it can make a new image, of course. It can make architectural solutions. Some of my students have an interest in architecture, so they like to build things like these. So you can do really pretty fun stuff. And again, it's combining now ideas and thinking and processes from very different fields, like an image, a cube. In the paper, actually, I took a picture. We had the solar eclipse last year, right? Last year, this year or last year? It feels like it was like 2 years ago. But and so I took a picture of the solar eclipse, and I asked the model to design a material from that. I didn't put this in here, but it's fascinating. You can do really cool stuff that previously only humans could do, right? You can look at something and then be inspired by that. Now I can have machines do this. I can also look at proteins, right? So I can give it a picture of proteins and let the model kind of reason over those images. So this is kind of like how our vision is to, we're using this actually in the agent models because so we can make a protein and we can make a picture using VMD, and then let the model look at it, right? Or make a trajectory file and things like, or a trajectory, a movie basically. Oh, what happened? Here we go. And so that's sort of important in the agentic framework that the model can sort of understand what it's predicted. I do fracture a lot, so yeah, we've done work on fracture, can understand these. So now shifting gears a little bit. So there's other stuff we can do with this framework, right? So when we have graphs are powerful. The graphs that I've talked about so far, many of the graph representation the model builds are abstract internally, right? So they make a sense of the world, but they don't tell us how they do it, right? But I can actually force the model to do it in a way I can read it. I can basically build graph representations in natural language or in symbols, whatever I want to put as a constraint. And so we have done this here. We built what's called ontological knowledge, which is really very closely to what we have done in category theory early on. Like I said, 15 years ago, we've built these kinds of things. So you take a concept, A and B, and you understand how they're related, right? Now, back in the day, we could only do this for one paper basically, and we spent a year doing it, or two, or a few months at least. But now with AI tools, I can scale this. In fact, I can use thousands of scientific papers, and I can build graphs of those. I can build ontological graph representations of every single paper. And of course, what happens when you create these, when you put them together, they become a gigantic graph because these papers aren't isolated, right? Most of the time they're connected. So there's a transitive property between them that, what I mean by that is that if one paper might talk about, graphene or mycelium and a silk protein, and it might talk about this in the context of, maybe a particular medicine. Another paper might talk about it as a mechanics application. Another paper might talk about it from a legal perspective. And all of these things are right? They connect in the graph. So this gigantic graph you get at the end is kind of overwhelming, actually. As just looking at it, just thinking about it, for me, it's like totally mind-blowing. But these are thousands and thousands of nodes that are all connected. We know the relationships, we know the nodes, the scale-free network, which you might expect, perhaps, I guess. But that's also really cool. But the most important thing is that this graph has really interesting properties, right? So we can mine this graph. So for example, I can say, I want to know how things are connected that I've never seen a connection. So this is kind of like going to the point where how do we model scientific discovery, innovation? Well, maybe that's one way of trying to do this, right? So you can create these abstractions of how knowledge is organized, and I can say I have sustainability and I have mycelium. How are they connected? And those are maybe more obvious, but you can do totally weird things. In fact, I did this in some of the others. I've done it totally randomly because all the things I picked are kind of related. So I did a completely random selection. I picked 2 nodes on the graph. It's a fully connected graph, so there must be a path between them. And so you can find these weird connections. You can understand how something, concept A, concept B is related, which you might not have thought about before. And what we can do with this is we can then, so whenever you make a connection between 2 things, or 3 actually, you can do this obviously for many other things, you get a subgraph. Now, this subgraph looks a lot less overwhelming. It's still overwhelming, but not as much as the big one, right? It's not hundreds of thousands of nodes and edges. It's maybe a couple hundred or 10, 20. And you can kind of see how things are connected. You can also understand, because of graph theory, you can mine the graph also for things like which nodes are really important and make the network really fragile, right? So those are potentially topics that you might want to pay attention to, or you might want to find highly connected concepts, like that have lots of different connections and so forth. You can learn a lot from these properties of each node and the edges, and you then use these graphs that you've extracted to reason over them. So instead of just asking the model to think about whatever its own representations, you give it these connections. And you can do this also automatically. So in this paper by my postdoc, Alvisa, I don't know if he's here actually. Maybe he's not. I don't know if he's here. He's probably not here. But he created this. He used this agent network model we developed. But instead of solving a problem that we already have, we use these agents to make problems, basically, right? So we basically use these agents to come up with scientific ideas based on these graph reasoning algorithms. And, again, so you kind of pick two or three. We did only two, but you can pick more than two, obviously. And we sample many paths. I mean, you can sample the most direct path, and that's okay. But we can also sample for indirect paths. I mean, I can develop an algorithm that will diffuse me to the other point I want to be at, but not in a direct way. And this kind of models, of course, scientific discovery. It's not like I know the answer at the path from here to here. I might kind of explore weird new connections. And so this is what we do here. And we let all of this be done by agents, right? So we have a whole set of AI methods that do kind of all these different graph reasoning tasks. And ultimately, they organize themselves to come up with an outline for a research idea, anticipated behaviors, novelty. And so we give some guidance to what the model should kind of come up with and think about. But the model entirely on its own kind of gets to work, basically, and figures this out. And it then writes this out in a paper. And basically, it's very long. These are 10, 20,000 word long documents. These are very detailed. Okay, so they're not like asking ChatGPT, give me an idea. But they're very detailed, very structured. Again, the model thinks about graphs, it thinks about the connections. This then, in turn, can become an input for the other agent network I talked about. Right. So if you confine the search space to proteins, you can say now I have a problem. Right. So psi agents is this model we call psi agents. You give that problem now to prod agents, and then this can figure out solutions. This is kind of like how this could come together in the future. This, we haven't connected them yet. We've done this independently, but where our next step will be to connect the two. And so now you're creating a problem, an idea, and you come up with a solution. And I should mention, this is totally scalable, right? So, anything computational is scalable, of course. Like you get access to big cluster. Now, instead of running, one idea per day, you can run thousands a day, 100,000 a day, and you can just come up with the most interesting things. And then you can rate them. I think I actually removed the slide from here, but we have a way also of, it's not on here, but of evaluating these ideas. So we have one of the agents has access to literature databases, and it will actually develop a numerical score for novelty and feasibility. So because, of course, you can come up with a crazy idea, but somebody else has done it already. It's not very interesting. But we can have an agent that has access to literature, and it can actually assess how novel this is. So this is not the complete thing, and sort of the latest model. We have another column, basically, that we can use. We can rank this, and this is really what we want to do. So we don't want to have 100,000 ideas. Well, test them can't. We have to make the most promising ones at the end. And once you get to the point where you have an idea you like, just to show you kind of what these models can do today. I mean, even today already, we can make the model, give us a visual representation of what it has designed, right? So in this case, it's a mycelium collagen composite the model has come up with. It makes a picture, and it can explain to us what it has made, right? So it can associate the different features, the design features, the components, the kind of the faces in the material, and its function, and it can provide quite a lot of details. So the details very high, right? So it's not just use some collagen and mix it together, but actually has very specific instructions on how chemistry will work, functionalization will work, and so on. So this is sort of the result, of course, of having all these different experts, right? So having really good models that can solve very specific design problems or analysis problems, right, and physics simulators and all these things gets you a pretty comprehensive, very deep answer. And ultimately, even a manufacturing process. So this is something you can do at the end, right? You can make this manufacturing process as well. So now, I'm almost done. Okay, I think I'm timing was pretty close. So last thing is a little more entertaining, maybe. Well, I think other things, hopefully everything's entertaining. It was really fun. I think it's such a, I feel I have to say it's such an interesting time where we can begin to explore some of those things. There's lots of work left, obviously, to do this, but I'm very excited actually because it's something that I've been trying to do for ever since I did my PhD. Or actually, I was an undergrad student, but can never really do it. Connecting these different ideas and fields, but now we can, and it's just so exciting. So the last thing I want to show is something a little crazier, and I think we talked about it earlier, is connecting with music. So one of the things you can do also with AI is to solve problems that maybe are not very important for any real problems, but maybe they are actually maybe even more important because they tell us something about the world that really ultimately science should explore, right? So what we did here is to ask the following question. We have all these translations of, let's say, known knowledge, right, and getting new ideas. Like this was the last example, solving a problem, like very tough stuff, but it's, very direct and very obvious. Here we're asking a sort of a weird question and saying, can I take music and actually represent music as a material, and vice versa? So what it means is it's a latent representation. So those of you familiar with machine learning, right? So latent representation means I'm encoding myself, in some other representation, maybe, compressing the information, hopefully. I'm lossless compression, but actually it's supposed to be lossless. But sometimes it's also we have loss. But ideally you have a representation in latent space that is has more information, is more elegant, right? And then you can do vice versa. So usually a latent space you don't really use it for anything. It doesn't look pretty. It's not really interesting. It's useful. Here, I say I want the latent space to be the other representation. So I want the music to look like a material and the material look like music. So I can listen and look at both and make them actually in the lab. And so this is the problem we looked at here. And this actually sort of comes back to isomorphism, right? So what it means is that I find a way of mapping my function of music, my function of material into one another through the isomorphism, which we can painfully create manually in category theory presentations from papers and understanding. But I don't want to do this because I don't know the answer. In fact, I do not know how to make music into protein and vice versa. This is totally unknown. And it's not really easy for humans to solve this problem, actually, right? So, and there are many others like this, of course. So the question is, can the machine do this for us? And so we built a machine that can do this. And it can kind of go both directions, as I said. And so this kind of is what the model will do. Now, and so how it is done actually is by using, again, no surprises, a multi-agent system. So we have 4 agents here, and they solve this problem basically as a team, right? And so you can see the power of this multi-agent framework is extremely powerful. And the idea is basically that we have an agent that converts music to protein, protein to music, another one. And then we have agents that sort of, give a reward signal or penalty signal based on how well the translation has been completed. Okay, so this is sort of the idea of a little bit like reinforcement learning like we did for the thinking and reflection process. We use reinforcement learning where you don't teach the model how to do things exactly, but you give rewards for good and bad answer or gradients of that. And so we do this here as well. And so what comes out of this is some really fun stuff. Like we can do this, in fact, almost lossless, actually, which means the model has found ways of mapping music sequences to protein sequences in both directions. So I take a bunch of music, I can make protein, I can take protein, I can make a musical score. And to show you how it looks like, so this is sort of a visual that's in the paper, this is just a graph, but it shows you how basically the raw numbers look like, right? So if you print the sequences and their notes and their proteins, and obviously there are more notes than there are protein amino acids, right? And model can totally understand that, right? So it plays with all the different dimensions and kind of figures out how to make something that's actually a protein sequence. It looks like real protein sequences. It's actually fake. It's a new protein, never before been seen. But it represents that particular musical sequence and the other way around as well. And you can see how this works. So if you do the cycle translation, meaning you go from one to the other and back, it should be the same. And it is. Right? You can see there's a pretty good job in both directions. So pretty amazing, actually. And then here's a audio of not exactly this, but it's another translation. So I do a lot of work in music, and this is a different problem. It's not using this model, but it is one where we do recursive translations, actually. So what you hear in the background is what I call deep aria. So it's a conversion of, you might know Bach's Goldberg variation, right? And the idea of Goldberg variation actually was like a music made to get some king or princess, I guess, to go to sleep at night, right? It's sort of this repetitive, mathematically organized music, variations, many variations. We played on this by creating variations, not based on mathematics, like Bach did, but actually creating variations by translating the protein into music and back. And by using a little trick, when you fold the protein, you create new information. That's behind that. I don't have any details here, but you can read up on it if you want, or I can talk to you about it. Basically, when you fold the protein, you have new information that comes from this process. So the music becomes enriched, and you can do this for crystals. So the proteins become more complicated, the music becomes more complicated, and what you hear actually is the music. But these are the proteins sort of as they go through this iteration. And it's pretty fun. So that was the final, as a entertainment part, right? And then with that, so thank you very much. It was fun to talk, and happy to answer questions, of course. Thank you. Good.
Thanks so much, Markus. Let me see if I can grab another mic.
Sure. Yep. Sounds good. We can just shout it out, maybe. I mean, I can repeat the question, and so for the audience, yeah.
Okay, maybe I'll ask the first question. But I'm really excited about the music part. I was wondering, capture things about the food, or is it mostly looking at?
Yes.
Wondering, like, is it a global or music?
Right. Yes, yeah. So the translation that we did, we look at only sequences, but in this model here, which I did not go into the detail how we did this, but yes, actually, it does actually look at the connections. In fact, that's how we enrich the music, is that when you have a sequence and now you're making it into a folded structure, we add information because of context. So we're looking essentially at the contact map, okay? And so this this is a mechanism we use to create counterpoint, right? So what you heard, the earlier model I showed, the totally autonomous discovery, just looked at sequences, and it translated sequences to sequences. It didn't account for the 3D structure. We could actually add this too, but we didn't. Here in this algorithm, we actually create, so in music you have a melody, right? And so the way you make things more interesting is having multiple instruments maybe, or multiple melodies playing together. And that's usually, so traditionally, or in some theories, it's referred to as counterpoint, right? So you have multiple melodies that play together, right? And when you fold a protein, you can kind of imagine this is the process. So the protein is unfolded, it's just a melody. And when you fold it, you can hear things that are close by that might come from a very different part of the protein. And so we have developed an algorithm. This is an algorithm that we developed actually for this process. So it was not AI discovered, but that can capture this. And so now you're creating actually a representation, a musical representation of closeness and connections and contact. And this is how you then create notes. The notes, now I'm telling the whole story. So now the notes now are again, a sequential event. I can translate those back into a sequence. That sequence is much longer now because it has multiple notes played together and against each other. That creates a more complex protein. More complex protein becomes a more complex structure, has more context. So the music becomes, recursively more complex. And I did this actually. There was an event we had at MIT here, CAST. You might know CAST, this Art, Science, and Technology. They had this event where they had a panel on, it was called Deep Time, and they gave all of the speakers the instruction, talk about something deep time. And I said, what do you mean? Like, well, you figure out you can decide what you mean by that. And so my idea was basically to find a way of letting, the protein sequences talk to the music Bach created. And you kind of like, so expand on what Bach did with the variations. He did it purely mathematically. He just used math to make the variations. And he thought it's very boring and make it basically a lullaby, I think it's called, to make people go to sleep. It's actually very beautiful, actually. It's not necessarily, it doesn't make you go to sleep, but it's one of the most famous, brilliant pieces of music, actually. But But yeah, so we basically, instead of using math, we used protein folding to enrich the music, and that sort of talks about something. Protein folding comes from billions of years of evolution, comes from quantum mechanics. All the ways proteins fold are not just math; it's some other weird. We just found out, it has to be modeled by some other algorithms, I guess. We don't have a theory for this, but that can be captured, and so you can find a way of letting these things communicate. Like the Bach had no idea about proteins, and proteins had no idea about music, obviously. So how do you connect the two? And this is my interpretation of deep time, anyway. But yeah, that's how we did that. So you create this recursive way, and you can make it increasingly complex. And what comes out is absolutely. I don't know how you've. So I played it to people that are that are in the kind of current contemporary composition. They love this kind of stuff. I played it to people that only know classical music. They said, this sounds weird. I said, yeah, of course. It doesn't follow the rules that classical music composition has. It exactly creates the rules from protein folding and evolution, and it's supposed to be weird. But so it has different reactions, but it definitely creates, some very. To me, it creates enormous, intense emotional responses, actually, because you know what's going on, and you can listen to the whole piece on SoundCloud. You can Google my name is SoundCloud. You find this piece, Deep Aria. You can just Google for Deep Aria, and you can listen to it. It's like 3 or 4 minutes long, and it like totally. To me at least, it just changes your mind, really. Yeah. Anyway, so yes, and you have to moderate. I don't know who's coming next. He's in my class, so he gets that. Yeah. Thank you. Yeah. 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 Right. Oh yeah. Oh no. Yeah. Yes. 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 No, absolutely. Yeah. I think right now we're trained the model and we did this kind of expert system, but absolutely, when you have so what I showed the XLOR kind of conversation, right? That's sort of the thing you could figure out there. So the model can say, like in an agent system, I don't follow this predetermined path. I think about the problem, and I might find a way of getting a solution from a different perspective or a different angle. I might solve the design problem not in the way that the human might have come up with, but actually through some other elegant way. It might search for existing knowledge. It might search the internet, the papers. Yeah, exactly. Yeah. So that's what I'm talking about. So that's sort of the next level of reasoning. I like to say reasoning, then some people don't like reasoning. They say machines can't reason. I totally disagree, by the way. I think that we can, I believe, of course, we can model reasoning. If you can model protein folding, we can model reason. Okay, it's a little bit, maybe not in this group, but I was at a talk last week, and then people said, oh, we can't model reasoning. And I said, well, I don't know. First of all, we don't know. Anyway, that's a side thing. But yeah, no, exactly. So we want to build machines that can do that. Yeah, absolutely. And it's not easy, but the more you have to integrate all these different capabilities and let the model have the ability to reflect upon all these different options, right? And make connections between new ideas and old ideas, and then hopefully come up with those. Yeah. Yeah. Sure. Between different composers, you mean, or? Oh, right. Yeah, no, you're going to have, you're going to get different translations. So we did this only for Goldberg radiation. That was a data set. But if you use multiple, styles of composition, different styles of music, then the model will need to figure out to model this in the latent representation, which is protein space, right? And so I can tell you that in some things I've tried, not for different composers, but for adding things like timing, velocity of notes and things like that. you might come to a point where the model just doesn't have enough capacity based on the training data on either one of those two domains to actually make an accurate representation, right? Because it cannot figure out how to describe certain details in the space of protein sequences it has seen. So you might have to expand that, right? So if you make so what I'm trying to say basically is if you add, many different styles of music, you might have to add more proteins for the model to study to be able to represent all these different styles in the protein space, and vice versa. And of course, the challenge is there's no theory, so we don't know where the limit really lies. I mean, and the limit might lie not only in the representation space, but also in the capacity of the model, right? It might just be the model's not smart enough, so you might have to make the model, more complex to be able to understand more of the, subtle relationships. Yeah, but that is a very interesting question. I mean, we studied this actually, but it's pretty wide open to understand that. And of course, at the end of the day, I mean, this is pretty, abstract and very niche field. So but I am actually exploring that. Yeah. Absolutely. Yeah. Yes. Or back. Yeah. Yep. Right. Yes. Right. Yeah. I mean, so the collagen. So the question is how the collagen, how we validate it and how it generalizes. I mean, we took. So the problem is that in collagen, these kind of measurements, there are only a couple hundred actually in the literature total. So we used what we could find. It's like 300 or so. We had there was a new paper published while we did this work, which we then included, in addition to some other splits we did, testing splits, but we also used some of the new experiments they've done as a test case, which it worked really well for that. And then also David did some additional tests, a couple of sequences in his lab as well. So we played around with, both just randomly tested, generated sequences that other labs had made, to distributions from within the training data, like randomly selected, to actually designed proteins. So we made, using a genetic algorithm, we made collagen sequences at the extremes, right? So we made very stable ones and very unstable ones. And those all worked pretty well with the model. So the model generalizes pretty well, I would say. Yeah. I can't. I have to say I can't tell you off the top of my head, but it's in the paper. But I can, if you, I am happy to send you things. But yeah, I don't know exactly how we. But it was very. I mean, I can say that the sequences have varied quite a bit. That being said, collagen sequences have a certain pattern to them, right? But they have been varied a lot. I mean, I just can't quantify right now how much we varied them. Yeah, but they were pretty diverse sequences through the spectrum. Yeah. Thank you.
Towards the beginning of your talk, you sort of mentioned atoms out of a million,
right,
in effect, these little microscopic
right,
properties. I'm wondering, after hearing the talk, you relate this back to that concept, in particular with protein mutation, single amino acids. What do you think that we could use the kinds of models that you're developing to better predict single amino acid mutation?
Yeah, sure. I mean, from the design perspective, if you make a new silk sequence, they usually involve small variations to affect properties of fibers. So we know that. And for collagen, it's the same way. I mean, there's a couple of small mutations that make a big difference in how the collagen stability looks like. So yeah, absolutely. I mean, that's generally true. I mean, we can get some very good predictions, forward predictions, and very good inverse predictions. The broader you make the design space, the more you have a distribution. I mean, you might have a very general design tool, and it might work really well for some proteins and not for others. But if you do it for, like, the collagen example is one where we can do a pretty good job given the training data we have. We've done other work on these just predicting their strength, forward predictions. we can do a really good job with that. It's very accurate. It's like an R2 value of 95 or higher. I mean, so yeah, you can very accurately predict mutations and how they affect the outcome. Yeah. Yes. Yes. I mean, it's all right. Yes. Okay. Of course. Yeah. So I think it's all based on graph-based models. Okay. And so you want to be able to model the relationships of the whole sequence to itself, right? And so that's something we can model. We don't want to coarse grain them out. I mean, so a lot of early models have done like convolutional type models, and they have this problem that they basically you reduce the degrees of freedom, and they look at patterns, but then they don't understand how a single part in that pattern might actually play a role in the big thing. So the graph models are really the key to this. Yes, right. And for those, yeah. Sort of, in a sense, coarse-grained by neighbors. Right. The nearest neighbor. Yeah. Exactly. Yeah. And so I'm wondering if you could point out the difference between a graph like that versus the graphs that you're. Excellent question, actually. Yeah. So I should add this onto my talk. No, but so my graph is not constructed in Euclidean space, right? So it's not based on. I think I had it. Well, I don't want to go all the way back, maybe, but. Yeah, it's specifically not made so that I'm having a graph neural network message passing, right? So my graph can include this kind of representation, yes, but it can also include very long-range relationships. So it can basically account for the fact that, there is a correlation between this single amino acid in this domain and another one, and it just happens by correlation, dynamics, salt bridges, whatnot. That they actually are really important. So if they're both there or both missing or one, so it gives us some perspective. So that is also modeled in my graph, but it's discovered. My model creates a graph presentation based on the observation. So every time you ask a question like what's the stability, what's the binding affinity, whatever you're training it for, the question you're asking, the model will create a graph for that question. So this is what the model does. So that's a big difference. Yeah. So graph neural nets are great. We've used them also. But they basically mean, following. I mean, you have to know the graph, and the way we usually know the graphs is by Euclidean representation. I mean, basically spatially close, even chemically, but also spatially close, like a Fuller geometry, and that means that the model cannot really understand functional. So what I was trying to show in the beginning in category theory, that's the point of that, is that you don't say only neighboring words are related, but you, like in language or in algebra, they are connections, they're relationships that are singular, they're rare, they're very important, but they're very unique, and those are the ones we discover. So our model, yes, exactly, it discovers those graphs, but they're very abstract. But that's the point of those. Yeah, exactly. Yeah. Just not bias against your person. Oh yeah, sure. Hi. Sorry, I see if there's somebody there. Good question. Well, I mean, they're so there's a couple, obviously. One is that maybe it's an obvious one, but one that I struggle with a lot is the fact that as these AI models become more powerful, they make very powerful predictions, they become very hard for us to understand and follow. Right? So in the early days of AI, you could make a prediction, and you could pretty easily tell if it was wrong or right. And now the predictions are much more. The predictions are very complex, and it's very hard to actually validate or test or falsify them. Right? So sometimes it's impossible to understand how the model came up with this, and you have to actually make an experiment or do numerical solutions. That's a failure mode, I think, because at the end of the day, we don't know how well these models work in the edge cases, even though we make them better. But so testing them, and it becomes more and more difficult to actually understand how they work. Now we try to build them to be interpretable, like I showed with the graphs. This is actually one of the reasons why we do this, is because we want the model to tell us how it thinks. And there's an advantage to this because I can follow the logic, right? And we can train these models to use natural language, but use logical abstractions, but something that we can follow. And we do that exactly for this reason. But The other failure mode is, I mean, of course, as you get more multimodal, you need more data. And, sometimes you just don't have, obviously, more, all the data, and it becomes sort of exponentially more expensive, computationally. So that's another failure mode, is that you just have to have really big models, really big computers. Our way to addressing this is building these sort of modular approaches like I talked about. And so this is really built on, first of all, being in academia. Well, I think it's actually smart no matter what, but it's, you want to build these models that you can build up, make them more complex, and you can understand them better. But there's a failure mode in that you make models really complicated. You want to be able to, you have to have certain levels of data, like for papers, you have to have, if you want to connect different areas of research, you have to have thousands of papers in different areas. It might be difficult to collect them and to get this. And there's a question of resources for one, I mean, really, yeah. And there are probably many other failure modes, and those are just a couple of things I can think about. But I mean, the other, I guess, one challenge is, maybe it's not a failure mode, but it's like we work with David Kaplan a lot and some of my other colleagues. Making the protein in the lab is not a failure mode, but it takes a long time. So we have cases where we made predictions and we did even MD simulations and all this, but then the experiment takes months and months to do, and that's something that so it's kind of like the human understanding, and it's not meant as a I mean, obviously it's just the way it is, but it means that your AI model becomes very good in predicting lots of different things, but the real, the experiment might be the time sink, essentially. It might take you years to actually get the validation data. And that's sort of a failure mode in the sense that, you want to actually make more predictions. But I think the way to get there, to me, is like we create confidence in the models. And the only way to do this is to do the experiment, right, and to do this work. But it means that, there's some sort of limitations in how quickly you can do things. If experiments could be done more quickly, we could, progress so much faster. And people are working on autonomous stuff and things, which is really important, I think. Yeah. Hey. A lot of questions. Yeah.
Very cool. Especially that it explains what your pathway from A to B and all kind of problems that
Right.
answer the question. Talk about expert agents, and I'm curious how Markus society is dealing with stuff and hallucination.
Right.
And what you right is actually wrong.
Yes. Well, exactly. So that's exactly why we have the agents. So the agents have, sometimes they work together on a problem, but a lot of times they actually challenge each other, right? So we have an agent that will, so for example, I'll give you an example. Like I want to predict these, let's say the protein design problem, and I use Chroma to make a prediction. And I want this to be a stable protein. So why do I have the MD engine? Well, I have the MD engine to calculate an energy, right? Or do a couple of MD steps to see whether the thing falls apart. So it's exactly this. So the agents actually create confidence in the solution so that the model by itself, like ChatGPT, has no self-awareness. It just makes a prediction, and it could be totally wrong. It's very confident, as is any other model, by the way. I mean, it's not just ChatGPT. Any PDE is the same way, right? So people always pick on ChatGPT, but it's actually pretty much any theory. So so we have agents to reflect, like I said, in the thinking process, to basically think about, is this really true? Well, to really check the prediction, what are the tools I have? I can run MD, I can do a literature search, I can see are there similar sequences in nature, right? Things like that. So that's exactly the reason why we have agents, actually, is to be able to kind of negotiate the solution internally. And then you, as a human, get the answer, and you see, like you said, you get the trace of the whole discussion. Yeah. Okay. Yes. Well, we give instructions. Yes. We give instructions, and we basically give instructions of some adversarial relationships usually, so that they don't live in a bubble, right, and have an echo chamber, right? So they have adversarial relationships. So there's an instruction that says, you have to check the results, and here's some mechanisms, and the models will then figure out how to do this. Yeah, exactly. Yeah, and this is part of why the modeling in this process becomes, how do you create the system? How do you instruct the agents? How do you train them? There's a lot of stuff going on, of course, to do this, but that's exactly what we do. So they're instructed, yeah. Because otherwise they could basically cheat, and they could basically just tell each other, oh, it's amazing, it's great, kind of like an echo chamber, which, it's a very human thing. I mean, these agents are almost like humans. They if you let them just be happy, and create a, they don't really do the job. So they have to have some competitive relationships. Mm-hmm. Yeah. Sure. Yeah. Sure. Hi. Yeah. Thank you. Right. Yes. Well, so I mean, in the paper we evaluate, these ideas for novelty. We have picked a few of those ideas. Actually, one right now that one of my students is implementing, and trying to follow the recipe the model created. So we're doing things like that. But again, like I said earlier, one of the failure modes. I mean, not failure modes, but it's hard because you pick this, let's say, this problem, and when you actually go to the lab and you make it. To me, I'm a theoretician, right? I mean, I have some lab and all that, and I work with David very closely and other experimentalists, but yeah, it becomes very complicated and very expensive, so you have to pick very carefully. But yeah, I mean, we're trying to do things like that, and then I do it usually in areas that I understand something about, like I've worked on amyloid and graphene actually, and so there's some things that I can also help judge to understand what these things are and whether they're total nonsense or not, and this is how we can screen the predictions as well. I mean, no, I mean, it's once the graph is generated, you can do it pretty easily. Yeah. And it's actually, so like I said, so it's scalable in the sense that if you have, a big cluster, you can run thousands of these predictions in a day. Yes. Yeah, absolutely. Yeah. Yes. We've had lots of interest in this, and we got some industry interest as well, and I mean, we only do, research things, of course, at MIT, but we have done some of those graph constructions for totally different topics. For example, we have a project with TSMC, the chip manufacturer, is a totally different area, and they have their own kind of databases, right, on chip manufacturing, and we're building a graph for that, and we have had very similar good results. So, and this is an area also, they know a lot about it, obviously, so they like it, right? So they can get some. So they are, kind of, and this is a much more niche area than what I've been doing. Thousands of papers in bioinspired materials. It's very broad. Chip manufacturing is very, very tight, but there's a lot of complexity. And so I think the way to do it in terms of validating and doing is maybe being a little bit more modest and saying, okay, I'm not going to do the whole field, but it's even small, but it's large. But let's pick, a subfield, like maybe. Yeah, for example, right, exactly. And I think that's the way we're doing it right now. We're building a bunch of graphs for sort of niche areas, and then it becomes also more, it's easier to track. You have experts that really understand the topic, spend their entire life doing this, and I think that's the way to do it, yeah. But it's a big field. But yeah, it's very scalable once you have the graph, which takes a while to get. But I've talked to people, that are saying, what, we're going to give you infinite compute. Can you make, I said, yes. It's scalable. Even the graph construction is scalable because we're basically building it on transitive properties. So, it's like you can build them in parallel, basically, right? So you just have to merge them at the end. And we have special processes to do that so that the nodes that are similar are going to be one node. So then this can be done with natural language processing pretty easily. So yeah, you can just get a huge cluster and in theory take all the papers ever written. I mean, they're going to be very expensive, but it could be done. And then you can build a graph that is, connects the entire knowledge of the world we ever created. I mean, I've talked to people that want to do this, and I don't know. I mean, I can't afford it, but maybe they might be able to actually. So and maybe that's not the right scale to do it. Maybe I think, but yeah, you can scale it for sure. It's parallelizable basically, very easily. Yeah. Yeah. Thank you so much. Thanks for staying so long. Thank you. Thanks.
I'm not sure if you need to leave right away or not, but maybe.
Yeah, I have to.